Hi everyone, we are Innova Hub team and we are representing Innova-tsn on the SAS HACKATHON. Big cities such as Madrid have a huge problem with pollution and urban mobility. Although those cities usually have sustainable transport alternatives, some of them have an underperforming service and discourage people to use them. By using both technology and advanced analytics techniques, the service can be improved and optimized, and eventually it may help to change citizen habits regarding urban mobility. In order to have more humanized and sustainable cities, there are a few different alternatives to use, such as walking, ride scooters, use public transport or ride a bike. In Madrid, we have a public transport service which is called BiciMat and is provided exclusively with electric bicycles. Consequently, the aim of this challenge is to optimize BiciMat service using advanced analytics to study and predict the demand and to create forecast models to provide the number of bicycles demanded for each day and different time slots. In order to develop this case, we use three datasets. One of them is the bicycle data usage, another one is the information of the docking stations, and the third one is other variables, which includes weather information and special events. I hope you enjoy this video. Have fun.
To approach this exercise, Innova gathered a bunch of open data provided by Madrid City Council. This data allowed us to predict the demand of bicycles and identify possible improvements of the service. First, the dataset is prepared. Second, a demand forecast is worked out on a daily and hourly basis, applying different algorithms. And lastly, optimization phase will provide a better understanding and management of anchor availability and bicycle replacements. For the implementation of this exercise, Innova used some Jupyter Notebook Python libraries that are available in SAS via. For the implementation of the SARIMA models, we have used SAS Enterprise Guide for the data treatment and SAS Forecast for modeling and forecast. The data available about BiciMat service that has been used in this exercise is number of trips, departure station, destination station, duration of the trip, situation of the stations at date and the time, location, capacity of each station, and the number of bicycles available and docked. To complete this data, the weather forecast information has been added, as well as the Madrid holiday calendar. For the different data sets, Innova team picked the common historical data available for all of them. Some important information we gathered is 266 stations exist and 250 of them were active in that period. The bike capacity range per station is between 12 and 30 bikes. And lastly, 89% of the docks in the active stations present activity during the day. We wanted to analyze the closeness of BiciMat stations to other transport stations or office areas. According to this, we concluded that almost half of the BiciMat stations are within 1 kilometer radius from an office area and almost 60% within 1 kilometer radius from a transport station. The graph shows the daily average BiciMat users per month. We can see a huge drop in April 2020 due to COVID lockdown and a big drop in January 2021 due to a meteorological incident in Madrid called Filomena. In this graph, it is shown that the most demanded stations are close to the center of Madrid, the most touristic zone. The accurate forecast of plugs and unplugs in every station for each hour of the day is crucial for the optimization model. The basis is to analyze the historical data, identify trends and seasonal patterns. Also, other variables, such as the weather, are taken into account in the models. We have enough historical data to identify these patterns. We have information on plugs and unplugs for each station at each hour of the day for the whole period. However, the situation of the city lockdown, Filomena snowstorm, and some technical issues with BiciMat service altered the demand. Weather data such as rainfalls, temperature have an impact in the proportion of bike trips. It's important to understand the difference in the hourly patterns of plugs and unplugs depending on the day or season. For example, unplugged bike peaks that exist on weekdays don't exist on weekends when there is more activity at midday. There are also different patterns depending on the month. There are also differences depending on the station. Stations located in office areas have the peaks of plug in the morning, while the unplugs are more often in the afternoon. We have decided to use 4 different models to forecast the plugs and unplugs with a 1-week time horizon. In time series analysis, ARIMA models can handle data with trends, but does not support time series with seasonal components. To solve this, we will use SARIMA. In order to compare different strategies, Innova-tsn diagnosed an hourly model and a daily model for its station. Innova picked the daily model. To improve the forecast results, we analyzed other variables that could affect bicycle demand. To obtain an hourly forecast, we need an hourly profile to be able to disaggregate the daily forecast. We saw that bicycle demand is homogeneous, so we can obtain a disaggregation based on historical behavior. We used XGBoost for its good performance and facility to input external values. Light GBM was chosen due to the accuracy and its high efficiency of results. Lastly, LSTM is one of the forecasting techniques that usually presents good performance when dealing with sequences. We optimized the bike replacement process model based on bikes available, known demand forecast, and simulation of the lost demand based on different scenarios. For the exercise, we considered the hill climbing algorithm, the simulated annealing, and the genetic algorithm. After a deep analysis, we chose the simulated annealing algorithm. The optimization of bike replacement process involves minimizing the number of impossibilities. This will minimize the number of unsatisfied users. The constraints that are applied are: the number of bikes replaced can never exceed the capacity of the station and the dock availability at a certain time. There is a limited number of bicycles in stock, and there is also a limited number of vans to do the replacements. With ARIMA, plugs and unplugs are very similar, and the forecast is similar to the real data, except for specific days. Applying XGBoost, we obtain a good shape in all 3 validation sets. This algorithm shows the best performance for 88% of the station in the last validation set. The results for Light GBM have a good shape in all 3 validation sets. This is the best performance for 6% of the station in the last validation set. These are the results of LSTM neural network. As we can see, it's the model with the worst performance. We also analyzed the mean absolute error of each station provided by the 4 models we tested, and we realized that there was not a unique winning model. So we ended up selecting for each station the model with the lowest error. The main objective of the optimization is to satisfy the demand. 4 different days were considered, including the lost demand for these. The algorithm will deal with high values of impossibilities, sometimes over 1,000. We used simulated annealing. In the first graph, we can observe the rises in the objective function, where worst solutions are being accepted. In the second graph, we show the best solution obtained so far. The execution time is associated with the evolution of temperature, usually around 5 minutes, stopping the process if it reaches 10 minutes. The results obtained on a daily level are very good, reducing the initial impossibilities by around 87% without reaching the maximum limit of replacement. This means more than 1,000 satisfied users per day for BusyMath services. Here are the results at the hourly level. The first 2 graphs show how the replacements have a greater effect from hour 4 onwards. More than 80% of the impossibilities were solved. The last graph shows the existing replacements versus the maximum repositions, always respecting the restrictions. We can see how there are more replacements in the first hours, trying to compensate for the fact that there are fewer possibilities of solving the impossibilities. Finally, we analyze the impact of the solution reached at the stations with the highest demand. For most of them, the number of impossibilities is reduced to 0. The second graph shows the percentage of impossibilities that are satisfied, with an average of 91%, as well as the replacements that have taken place in each station.
Variables related to the weather are assigned on a daily basis and in a central point of the city. The availability of these variables split by hour in each city zone could improve the performance of the model. Hourly disaggregation to split the daily forecast have been made in a naive way, just considering the average distribution of a concrete period per each station and day of the week. It would be possible to apply other techniques such as generalized linear models to make this split and obtain more accurate results. Using exponential smoothing and inputting null values in the past due to exceptional events such as COVID lockdown or PTMAD issues could be another way to improve the results. Use of walk-forward validation to update the model with the values of the previous day to get more accurate results. The spoiled solution provides a resource to the BCMAD management system that informs of the replacements to be made at each station throughout the day. This improves the service provided with a specific objective to avoid situations in which the user cannot make a trip due to the unavailability of vehicles or docks. The integration of the solution with the BCMAD management system requires that, in addition to provide the number of supplies per station, report the van route to make these supplies. This route should be based on the available resources and the standard resources as number of vans for transporting bicycles, number of workers per hour of the day, among others. Finally, we get to the conclusions. They are classified as demand and forecast conclusions and optimization results. Firstly, and regarding the result of demand and forecast models, we can conclude that the exploratory analysis has provided crucial results that has helped the team to approach the modelization strategy. The most important feature for the machine learning models are the lagged variables and the day of the week. Nevertheless, some external variables improve the performance of the model. Those variables related with the weather, especially precipitation and temperature, are the most relevant. Having them split by hour could improve the results. Furthermore, the optimization has shown some results that are worth highlighting. Firstly, the execution times of the optimization model is between 5 and 6 minutes. It allows us to obtain a quick solution that can be integrated rapidly in BCMAD systems. If BCMAD is to follow the recommendations of the model, the impossibilities will be reduced by an average of almost 87%, which translates to more than 1,300 satisfied customers. Given the difficulty to make replacements during the night, the majority of the impossibilities occur during the first hours of the day. Finally, in the 20 dock stations with more demand, impossibilities are reduced more than 90%. Thank you for watching, I hope you enjoyed the video and see you in another one. Bye.